Momentum review. So momentum is mass times velocity. This is a vector quantity. So we're looking at head-on collisions for the most part. It's just a one dimension. Collisions is the scenario that you care about for momentum and momentum conservation, because it turns out for a closed system that momentum is conserved. Therefore, if you got two objects that are boing, rebounding off each other, if you add up all of the momentum bits before the collision and all the momentum bits after the collision, they should equate. That's what conservation is. Now, these objects might be made out of different materials, so they might collide with each other differently. You might have something that's pretty bouncy or something that's not so bouncy. And here is the not so bouncy situation. If they collide together and stick, that is called perfectly inelastic. That is like one boundary condition on how this collision could play out. And you just modify that original formula just a little bit. It starts out the same way. But then after the collision, you got the two masses combined, make one giant mass, moving at one common final velocity. If AP asks any particular type of collision, they do like inelastic collisions because the math is real straightforward. So you might be asked a math question that involves a perfectly inelastic collision. Okay. The opposite of perfectly inelastic is perfectly elastic. That's perfectly bouncy. And here's probably as close as I can get to that. So, ooh, look at that. Okay. Now, what's special about this collision, like from a physics point of view, is that not only is the momentum conserved, which is universally true for closed systems, but also kinetic energy happens to be conserved, again, only for this type of collision. Now, if you run conservation of momentum and conservation of kinetic energy, because it's elastic, make a system of equations out of that, then here is always the solution to that system of equation. Now, this was the velocity of object A post-collision. That's what F is final, like post-collision. Okay, so this is always the answer to that. Now, you might, if you take physics in college, there's a good chance that you'll be asked to solve an elastic collision. And if you have this formula in your back pocket, then you'll save yourself a lot of paper and a lot of time solving it. AP almost never asks questions about elastic collisions. If they do, it's usually something real straightforward, like one object's at rest, one object, same mass, runs into it, in which case they just exchange velocities, something like that. It's usually about as far as AP goes asking that question. Okay. The information that's missing from this page is, well, what is the post-collision velocity of object B? Because nowhere on the, here's VB final, but nowhere in this expression is VB final. So if you solve for VA final, one way you can get VB final is to plug all these numbers in here, like this number would go right here, and then solve for VB final. Or you could do same thing here, solve for that VB final. Or alternatively, you could just swap the definitions of A and B. Your VB final is VB initial, mass B minus mass A, to mass A, velocity A initial, and then the sum of the masses down here. Okay. So there's a few different ways to get that. Now, how could you quantify? How could you quantify how bouncy is a collision? Okay. So the physics term for this is coefficient of restitution. It's the difference in velocities after a collision compared to the difference in velocities before a collision. Now, if you just run the numbers, it'll naturally come out to a negative value. So you can either take the absolute value, or you can slap a negative sign on, or you can do what I did here, which is that I did B minus A on top and A minus B on the bottom, right? So you got final and then initial, right? So that you come out naturally having a positive value for this. Okay? Now, the coefficient of restitution is going to be bounded by, that would be 0, because you have 0 difference in velocity between, say, this object and this object after the collision compared to some velocity before. Or it could go all the way up to 1, which would be pretty close to this right here, where the difference of velocity between the object after compared to before is like the same. So you get like 7 over 7 could be 1 with that. Now, AP is not going to ask about this. I've never seen AP ask about coefficient of restitution, but I always want to teach that because I think it's a pretty cool thing to know. It's like, how do you quantify how bouncy is something? Right. And then pretty common coefficient of restitution might be something like 0.7 or something like that. You can also alternatively find this by here. You guys know that the crash speed is going to be square root 2gh, where h is the drop height, and the rebound speed would be square root 2gh, like rebound height. So you can take the ratios of the heights, then take the square root, and then that will also represent coefficient of restitution. Right, but here's something that AP will ask about, which is impulse. So impulse is a change in momentum. Hey, change of momentum could be mass times change of velocity, and that's caused by a force acting for some time interval. Now, if you look really close, if you solve for this force, suppose you take this time interval and you divide it down here, mass times change of velocity over change of time equals force. Okay? Hey, change of velocity per change of time, that could be an acceleration. That'd be mass times acceleration as a force. F equals ma. Hey, that's Newton's second law of motion. So the impulse formula is one step away from Newton's second law of motion. F equals ma. F equals m times delta v over delta t. Okay? Now, graphically, on a force versus time graph, it'd be the area under the curve. Now, if you have a constant force, that's going to create a rectangle shape. But really commonly, you'll see these like triangle shapes, right? So if you have like a bat and a ball, right? And here comes the bat, here comes the ball, and you do it in slow motion. Oh, right? There's the point where they first make contact, then the bat pushes maximally against the ball, okay? And then finally the ball rebalances and then leaves contact with the bat, like, right at this point. Right? So there's like a variable type force, but it would just be the area under the curve. Now, this looks pretty similar to work is the area under force times distance. So if it was force versus distance curve, the area under that would be the change in energy, like the work done. But a force versus time, we're talking about impulse, the change in momentum.